So we've looked at some of the stuff on the periodic table, but there's more trends that we need to look at. So the first one, most of us are probably already pretty familiar with. You have certain categories of element on the periodic table. You have your nonmetals. Notice that hydrogen is one of the nonmetals. You have your metalloids, and then you have metals. It gets more classified than that, but this is the most simplistic breakdown. To go just a little bit further into those groups, you now have these. So you have like your alkalines, your transition metals, your rare earth metals. You have your other metals, you have your metalloids, you have your nonmetals, you have your halogens, and your noble gases. Each of these have their own similar characteristics. They're groups that have their own similar characteristics, and you need to understand if I say an alkali metal, which ones I'm talking about, an alkaline metal, or any of these. So make sure that you get a basic understanding. A good periodic table will already have these things labeled for you, but you need to have a general understanding yourself. Now, when we talk about trends of the periodic table, we don't just mean some color coding that somebody did a while back. It's actually set up in this funky looking design for a reason. It indicates a number of things as you move along it. The first one we're going to look at is atomic radius. Now, if you want to hear a very in-depth thing about atomic radius, because we have electron clouds and it doesn't have perfect little spheres like people think of. So when you think of, ooh, here's an atom and this must be its radius, that doesn't really make sense because it's not just an atom, it's a cloud. So really you have whoosh all around, and then somewhere in the middle you have a nucleus. And so it's not as clear cut as people think, and there's different ways to figure that out, but we can tell you. The basic thing, or the video I'll link to will tell you more in depth, but the basic thing you need to know is when we're talking about this, we are talking about the size of the atom. And the overall size of it tends to increase as you go from right to left and from top to bottom. This is just a greater visualization of that atomic radius, and you can actually see them getting bigger as they go from right to left and from top to bottom. Like I said, I will put some other links on there. This is about a 10-minute video where they explain in Khan Academy the whole thing about how it's not an exact thing to find the radius, how they might go about doing that, and what this actually means. I think it's simple enough to say, look, go right to left, it gets bigger. Go top to bottom, gets bigger. Okay, so now it gets a little bit more difficult, but still about the same thing when we're talking about ionic radiuses. Now, it's a little bit more difficult because we're talking about cations and anions, and so there's a difference between the two halves of them ever so slightly. We're still talking when radius is about the distance from the center of the nucleus to around your cloud boundary. What you need to understand is that the charges change as you go across the periodic table too, or not necessarily charges because all of them are neutral, but its tendency to go to a charge. That's what we were talking about last time about its oxidation number and valence shell electrons and things like that give us that oxidation number. So if you remember, your oxidation number goes with a +1, +2, +3, +4, and then it starts to go -3, -2, -1, and then 0. So with these, you can start to see that with those, you're increasing with the positive charge here, and you start with a more negative charge here and go to a less negative charge here. So you're still actually increasing in positivity. Now, the more positive an atom is, the more it can pull those electrons into it. So if you have an atom that, let's say, is +4 and only tends to have 2 electrons outside of it, then it's going to pull, because it's +4, it's positive. So +4, it's going to pull them in a little bit more strongly than something that would only be a +3. So if you had a +3 over here, they would be slightly further out because you just don't have as strong of a force pulling on it. And that's all that really means, and that's how that trend works. So you can see with cations, you're going to increase as you go from right to left, and you're going to increase a whole bunch as you go down because you also have greater shales. There's more things on them there, okay? So it's pushing it further out, so you're going to get in a larger radius. So less positive means that it's going to get bigger because they can go further away, and more shelves mean it gets bigger. It's the same basic principle for these, it's just they're all dealing with a negative energy, so it's less positive here than it is here. So kind of think of it the same thing. The more positive is, the more it's going to pull in. Okay. This is just a better visualization of what we were just talking about. So now you're looking at our anions and our cations. So when I said that it's less positive this way, so it's more positive from right to left, right? So fluorine is more positive than oxygen, even though both of them are negative. So the more positive it is, the closer they're pulled together. In the cations, it's real easy to see what's more positive because they're all positive. And so it pulls it closer in, but then more shelves means bigger atom. This is another link I'll have. They have about 11 some minute explanation of what I just said. Now, as we're talking about these trends, I think it's very easy to get confused, especially when people overcomplicate them. So I'm going to try to be simple. Now we're talking about an ionization energy, not an ionic radius, but energy. So before we were talking about the actual size of the atom, now we're talking about an energy involved. In fact, it's the amount of energy needed to remove an electron. So the way I think about this is if you think about picking an electron off of an element, you're going to want it as far to the left and as far to the bottom as you possibly can, because it's going to be easiest to remove electrons from those. In fact, that's one of the things that makes those kind of dangerous, especially down here where we have like uranium and such. Though they are a little bit radioactive, it's also very quickly to give off electrons because it's not very close to it. And you think this makes sense with what we just learned about them. If you get bigger atoms as you move down in energy levels or down in periods, then they're going to be further from the nucleus. An electric charge or a negative charge that's further from a positive charge is going to be easier to pull away than one that is very close to it. So going up requires a lot more energy to remove that electron. In the same instance, though, we said that those that tend to hold on to it, so they have a smaller radius because they're pulling it in tighter, and it's basically a greater ability to be positive, is going to hold on to it a little bit tighter. So helium really should be our most difficult one to remove an electron. This is a better visualization of what I was just talking about, and so you can see exactly what I was saying. And notice that it's not perfect. Some of these look about even. Oxygen even looks a little dim within, but that's why we call this trends. As you move to the right, it tends to take more energy. And notice all of our noble gases, they tend to be the ones that are hardest to remove electrons from for each of their periods, right? But also, the smaller atom you get with the less rings, it's holding onto it tighter. So as you move up, you're also getting more difficult to remove electrons. So that helium is our absolute best. Notice, though, that hydrogen actually does stick away because it only has one electron shell. And so they're all pretty close to the nucleus anyway, and there's going to be a lot of attraction there. Here's another one of these that I'll give a link for later. A lot more explanation. Now this is where people start to get confused. We're now talking about electronegativity, and if you notice, it is the same trend as the ionization energy. But when we talk about electronegativity, instead of talking about how much it wants to hold on to an electron, we're talking about how badly it wants to steal an electron. And this one's a slight lie because, as we'll see on a different visualization here in a minute, these noble gases, they don't actually want to take an electron. And so they actually have very low electronegativity. But all of the rest of them follow the same trend. So we still say that's the trend over the periodic table, is the more that you go up, so you're getting closer to that nucleus, the more it wants to pull an electron away. But also, the more you go to the right, and so you get to where these are trying to fill up that outer valence shell, and you get these things that are wanting to take an electron more. And we call this its electronegativity. So it's stealing an electron this time. Which one's more likely to steal an electron? Okay. Notice in this better visualization that the noble gases, it has it dropping off. That's because, like I said, noble gases, they're happy how they are. Their valence shell is filled. They really don't want to take or lose an electron. So they have a lot of strength to hold on to their electrons, but they're not really going to try to pull another one away, because that would mean starting a whole nother shell, which we'll talk about in a little bit. There's that trend though. You see how it does increase as you go up the periods and as you increase in the groups. All right, another link that I'll add. Now the last real trend that we want to talk about is a metallic characteristic. If you noticed in that first thing I showed you with the periodic table, most of our elements are a type of metal. They're either a metal or a metalloid. So that means that there's certain characteristics we need to think about when we think about metals. Things like shiny, malleable, does it conduct electricity? All of these different things relate to being a metal, okay? Let's take a look at this trend. So here's that trend of your metallic characteristics. Notice it's opposite of our electronegativity. So you become more like a metal the more you go to the left and the further down you go. And says things like explosion and the idea that it's a reactivity, because one of those properties of metals is the ability to conduct electricity or to transfer electrons is what it's doing. So think about this. The easiest one to remove an electron from is going to be the most metal-like, because it allows electricity to move freely through it. And electricity is nothing more than the flow of electrons. Now, this also should make sense from the very first slide that we looked at about the periodic table, because if you remember, we had transition metals, alkaline metals, rare earth metals, then we had our other metals and our metalloids until you got to our non-metals and our noble gases. So only this small section here is not even metal at all. The rest of it starting to show metal characteristics with the metalloids. You get some more in your other metals, then your transition metals, and of course your rare earth metals and your alkaline metals. These become very reactive and are used in batteries a lot because of that. So this is the general trend if you think more metal-like, and we'll talk a little bit more about what that means. So this is just one last chart that tells you the basic same thing, increasing metallic characteristics as you go from right to left and from top to bottom of the periodic table. Notice it leaves off the rare earth metals, but they're still considered in there in that trend. I think the important thing to remember about metals is they actually have what we call a sea of electron the more that they're there. So we think about having these energy shelves, but with metals, they tend to have what we call just spaced out nucleuses, right? And then you get electrons that they tend to already share, and they don't just orbit one, but they flow around all of them freely. It still keeps a balance in place, and we can still look at them as individuals and say they're in certain orbitals and shells and everything. But if you're talking about a true metal, you're talking about a free flow, or an electron sea, as they often call it. And so they don't have to really be owned by one nuclei. Which is what makes them conduct electricity, which makes them malleable, which makes them have a number of different characteristics that we associate with metals. So this electron sea is really the thing that we really want to keep an eye on when we're talking about metallic characteristics. And it increases as you go to the left and as you go down the periodic table. All right, I think that's all for this time.